This is How to Math with Dr. Ian Lundholm. In today's episode, projections and planes. All right, let's get this going. Today should be a fun lesson, even though it's probably going to be pretty long. There are some really interesting problems that we're going to do today, starting off with the dot product, and then we're going to do a whole lot of applications of the dot product and even into the cross product for finding distances and finding shortest distances and all that kind of stuff, mainly in three-dimensional space. So our first definition is the dot product. It should be familiar from matrix multiplication. We use the dot product in our computations there. And yes, u dot v, that is a scalar value. You're just multiplying things together and then adding them. And to remind you that u dot v in this class can definitely be written as u transpose v. When you go through the multiplication of multiplying a 1 by 3 matrix times a 3 by 1 matrix, you get a 1 by 1 matrix as an answer, which is just a scalar value. All right, now we've got three vectors, u, v, and w. U dot v is a real number. Great. The dot product is commutative. Great. Dotting any vector with the zero vector is not the zero vector, it's just zero as a scalar. The dot product of u with itself is the magnitude of u squared, or the length of u squared. We'll get to see a little bit more about why that is. I mean, really, you're just envisioning it as the hypotenuse in a triangle, a right triangle. We've got associative properties. We've got distributive properties related to the dot product. So all of these properties that we know and love work with a dot product. And so we are familiar with the way of computing a dot product. Come on. Let me go back, please. Thank you. Dude. Anyways, we're familiar with this way of computing a dot product, where we multiply and add, but there's another way of computing the dot product, which we're going to look at right here. Dot products can actually be very helpful when you are interested in finding the angle between two vectors. So here's an alternate way to compute the dot product, u dot v. It is the magnitude of u times the magnitude of v times the cosine of the angle that is in between them. And we're always looking for the angle that's in between 0 and pi, just meaning the smaller of the angles that you could make between two vectors u and v. Yeah. Right, and the proof of this would use the law of cosines. As we'll see later, when we start projecting things, I've got another way of kind of looking at this and understanding what the dot product really means. So hopefully I remember to explain it then. I will explain it then. Let's keep going. Let's think about what the sign of the dot product would be given two vectors u and v. If the angle in between them is in between 0 and 2 pi, cosine is a positive number, so the dot product should be positive as well. If they are at a right angle to each other and the angle's pi halves, then cosine is 0 at pi halves, and that makes the entire dot product 0. So this is one of the most useful properties of the dot product, is that if we can find the dot product between two vectors and that dot product equals 0, we know that the two vectors are perpendicular to one another, or in this class we're going to use the language orthogonal. to one another. And then the dot product is negative when the two vectors are kind of pointing in opposite directions. Not necessarily totally opposite. They'd be totally opposite if the angle was pi, but yeah, the dot product will be negative in that case. All right, and that is just saying that u and v are orthogonal if and only if their dot product is 0. That's going to be super helpful for us today as we keep using dot products. All right, and so if we were given two vectors and we wanted to find the angle in between them, really all we need to use is this new way of computing the dot product. All that has happened here is given the dot product of u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle in between them. All I've done is solve for the cosine of theta, and then, by dividing by the magnitudes, they get 1/2, and you can determine that the angle there is pi thirds because the cosine of theta is 1/2 at pi thirds. Cool. So it doesn't take a ton of computation to figure out what the angle between two vectors is. And here's another instance. If we were to just maybe start doing this on our own and multiplying 7 times 1 to get 7, -1 times 4 to get -4, and then 3 times -1 to get -3, adding all those together gives us 0. So this dot product between u and v is 0, and these two vectors are orthogonal. It's just that simple. Okay. This one is a little bit more interesting. Find all the vectors that are orthogonal to both u and w at the same time. So what we can do is set up a couple of dot products here. Yes, there are infinitely many such vectors. All of the vectors that would be orthogonal to these two would be, pointed in the same direction. They'd just be scalar multiples of each other. So here are a couple dot products. We can take v dot u and we can take v dot w and set those two dot products equal to 0. Now those look pretty familiar, right? We've got, sorry guys. We've got a couple of things here that look like planes, right? And so essentially what we've found here, dotting v and u, we found a plane who's going to go through the origin, and dotting v and w, we found another plane that's going to go through the origin. I will go into this more deeply later, but yeah, you can envision planes as a collection of points whose dot product is a certain value away from the origin. So these ones just happen to go through the origin. Hold up. And so we would be able to solve the system using row operations. There's our augmented matrices there. And we could come up with a solution there. And this is one vector that is orthogonal to the first two vectors that we were given. So that's pretty cool. Here we go. And if we wanted to figure out if these 3 points were the vertices of a right triangle, really all we'd have to do is do 3 dot products to see whether any of these sides actually were orthogonal to each other. So we create the 3 vectors that would go along each side connecting the vertices. and then take 3 dot products. None of them are equal to 0. So that triangle is not a right triangle. All right, here we're going to do a little bit more geometry. We have a rhombus. And a rhombus is special because all of its side lengths are equal. We're going to have to use that in this solution. So we're going to prove that the diagonals of the rhombus are perpendicular. So we're creating this rhombus so that, use one side, v is another side. They're of the same length. The diagonals here are u plus v and u minus v. To show that these are perpendicular, it would make a lot of sense to take the dot product between these two vectors, u plus v and u minus v, and set that dot product equal to 0 and see what happens. So, it will be nice if this turns out to be 0. So we're taking the dot product here and using the distributive property. Then the middle terms cancel out nicely, u dot v and minus u dot v and plus u dot v. And all we're left with is the magnitude of u squared minus the magnitude of v squared. And since this is a rhombus and u and v are of equal length, then that right-hand side is 0. So the diagonals have a dot product who's 0 and the diagonals are perpendicular. Okay, here we are to projections. We've got two vectors, u and d, and we want to express u as a sum of u1 and u2, where u1 is parallel to d and u2 is orthogonal to d. And so this is what I was hinting at earlier. I want us to ask the question, what would the dot product between u and d look like if d is a unit vector? So let's, for just a second, pretend that d is a unit vector. It's of unit length. What would u dot d look like? Well, we take this dot product, we use the formula, but the magnitude of d is 1, so that can just, drop out. We're multiplying here. And we get the magnitude of u times the cosine of theta. And that should be fairly familiar. I mean, working from geometry in the unit circle, really, the magnitude of u times the cosine of theta is just the amount of u headed in the direction of d. It's just this length. Let's see if I can do this. Oop. Yeah. That length, or the magnitude of that. And so the projection is not just about length. You actually want to find, the vector. We're concerned with finding the vector u1 when we're finding the projection of u onto d. And so again, if we were just pretending for a second that d was a unit vector, then the projection of u onto d, that's this notation here. It's the projection of u onto d. D is a subscript there. Would look like this, where we've got the length of the vector that we want, and we're scaling the vector that's going in the direction we want. And remember, we're still pretending that this is still a unit vector in that direction where we want it. And just to put this back into like a dot product kind of format, we can solve again for the cosine of theta using our dot product formula. And that means that changing the cosine of theta would be going to this whole part is what the cosine of theta turns into. But it's u dot d over the magnitudes of both of those vectors. And doing a little bit of cancellation, the magnitude of u over the magnitude of u, and the fact that the magnitude of d is just 1, we get this result that the vector here, u1, let's write that here, u1 is the projection of u onto d, and it's really just the dot product between u and d, if d is a unit vector. It's that dot product to get the length that we want for the length of u1, and then we multiply it times the unit vector so that we get the direction that we want. I think looking at it in this simpler case makes the next case a little bit more understandable. So let's go ahead and move on to the next one. Here I'd like us to no longer consider d as just being a unit vector. u1, the projection of u onto d, would be given by this kind of equation, where again, this is that length that we had last time. It's the length of u in the d direction. And we've appropriately scaled d by dividing by its magnitude so that this d over the magnitude of d is a unit vector. And then we multiply by a unit vector over here to give us the direction that we want. So unit vector in correct direction. And doing a little bit of simplifying here, we still have the u dot d on top. So that becomes this part over here. And then we have the magnitude of d squared on bottom, which is really just d dot d. This is kind of the easiest way to remember what the projection is for me. You take the vector that you want to project, and then the vector that you want to project onto, and you write that just a whole mess of times. You write it 4 times, but yeah, you're doing a dot product over another dot product, and then that is like your scaling factor. I wrote this again so that it wouldn't be so cluttered. This front part, the 2 dot products, that is your scaling factor on the vector d that, allows you to create the correct length for u1. Real quickly, we will skim through the book's explanation for this. It's a little bit more just, algebraic in nature rather than geometric. I like to think of things in pictures, but maybe you guys like to think of this as algebra. So if we wanted to figure out what the scaling factor here is to get u1 the correct length, I want you to pay special attention to this right here. T is that scaling factor on D that we want to use to stretch out so that we actually get the correct length for U1. So every time that you see T down here, think scaling factor. And so they set up this equation just by saying that U1 and U2 would be orthogonal, which means their dot product is 0. They change U1 into T times D, and eventually they arrive at the conclusion that U2 dot D is perpendicular, which makes a lot of sense because U1 and D are headed in the same direction. More lines of algebra, getting down to the same conclusion that I, had shown you before, that the scaling factor is really going to be U dot D over D dot D, or the magnitude of D squared. So that's easy peasy, right? I mean, if we want to find the projection of U onto D, this is exactly the formula that you want to use. Right there. It's just a bunch of dot products together, but super handy. All right, we're moving on. Here is just that in summary. If you want to find the first vector, u1, the projection of u onto D, you use that formula. And if you want to find the perpendicular vector, the one that's orthogonal to u1, this is the u2 in that picture that we just looked at, you just subtract u and u1 to get u2. It's just the difference of those two vectors. All right. Now we have two vectors again, and we want to find vectors u1 and u2 so that both of them add up to u, and u1 is parallel to v, and u2 is orthogonal to v. So this is what we would call an orthogonal decomposition, where we're trying to break u into its components, one that's parallel to v and one that's perpendicular to v. And in order to do that, we're just going to run through the same steps that we just looked at. To find u1, the one that's parallel to v, we're going to find the projection of u onto v. And that's what this looks like. We have the scaling factor out in front. And we've got that vector v that's in the correct direction that we want to head. And so that gives us the projection that we want. And then to find u2, all we do is take the difference between u and u1, because taking that difference gives us, the other piece that we're missing. I guess I could draw real quick. If this was u, and u1 was heading this way, u2 would be this piece. So that's just vector subtraction. U minus u1. And it might be the other way around. I think I drew it backwards, but it's okay. Same diff. Now we're going to be calculating distances in 3 dimensions. So the first one is we're given a point and a line, and we want to find the shortest distance from a point to a line. This is going to be important. It's going to be on our activity on Friday. So get excited for that. In order to find the shortest distance from the point to the line, we're going to do some more projecting. Here's our diagram, and there's our vector u. Our line L is here, and that's where we're going to create our vector u1, and this would be our vector u2 that's orthogonal to u1, just using the labeling that we've used previously. I'll try to label, all of these labels are with P0s and Qs and all that kind of stuff, and it's a little bit confusing, but I'll try to make connections on the way through this. But yeah, we're really just going to be projecting u onto the line L, getting u1. If we add u1 to the vector 0, 0 p0, the origin to p0, basically the vector version of p0, then we'll get q. And if we want to find, say, the distance between P and Q, those 2 points, that's really just the vector u2, or it's the length of that vector u2. And so that'll be pretty easy to do once we find the projection of u onto L. All right. Here we'll go on to the next slide so that we can start to see some math. Yeah, we're taking the dot product here. Well, we're projecting u onto the line L, which basically means that we're taking u and we're projecting it onto the direction vector here. The direction vector is the one here. Come on. Is this vector? This one is the one that is d, the direction vector for our line. So we're doing u dot d here. Or we're projecting u onto d because d is giving us the direction of that line. Okay, so that's what u projected onto d looks like. This p0 p vector is u. And this one is u1. So we're finding u1 right now. We find u1 over here. And then this one is locating, this calculation down here is locating q. So here we add, we add u1 to the vector version of p0 to get q. That's this whole piece. All right. And to actually obtain the shortest distance, really, that's QP, but that's the vector that we labeled U2. Again, it's just U minus U1 to get that U2 vector, and finding the magnitude of the U2 vector is what gets you the shortest distance from the point to the line. Okay, so real quick, let's just take another look at that diagram. We had U, we projected it onto D to get U1. To locate Q, we added U1 to the vector 0, P0. And in order to get U2 and the length of U2, we subtracted U and U1 to get U2. And then we could find that vector's length. Again, we're going to get more practice with that when we do our activity. So that should be fun. All right, and here we get to talk a little bit more about planes. There is a unique plane determined by a point and a normal vector. So a normal vector is orthogonal to all of the points in the plane. So the dot product between a normal vector and any vector in the plane is 0. This is okay. It's gonna make more sense soon. Let's keep going. Here, I actually just want to get it all out here, because this is what I said earlier. This is, an alternate way of looking at what a plane actually is. So down here at the very bottom, no. All right, I want freehand highlighter. This one. This equation. Looks like a pretty standard plane, right? Where A, B, and C are just coefficients on x, y, z. D is just some number. There is a way to understand what this is based on dot products. That left-hand side is literally the dot product between a vector containing the coefficients and a vector containing x, y, and z, the variables. And so the way that I like to summarize this is that a plane is a collection of points, so x, y's, and z values, whose dot product with a given normal vector, that normal vector is ABC, is some constant value. And I would encourage you to play around with this idea in GeoGebra, to actually make a plane with some sliders, construct some vectors here, using A, B, and C, using x0, y0, and z0, and just playing around with the fact that you can envision planes as a collection of points who all have the same dot product with a given vector. It's really cool. And the planes that go through the origin are exactly the planes whose dot product with that given vector is 0. Super cool. I love learning more about, an object that I've already been introduced about, but get to think about it in a completely different way. Cool. All right, next example is finding an equation of a plane containing a point and orthogonal to a given normal vector. So in order to do this, really, we can just use the different entries in that normal vector as the coefficients on our plane, and then finding the dot product between this point and the normal vector will be enough to give us our d value on the right-hand side. So the dot product between n and the vector version of p0 is just -8. And so the scalar equation of that plane looks like that. It's pretty cool. All right. This sentence is a lie. There are not two solutions to this problem. There's two different solutions to a problem later on. Maybe. I think. But I remember doing this problem, and there were not two solutions. We're going to find the shortest distance from a point to a plane, and then find the point Q that is closest to our given point P. All right. So we'll set it up like this. The main thing to notice is we want to find the distance between P and Q. If we can find some Q down here in the plane that is, perpendicular, and this line from Q to P is completely orthogonal with the entire plane. And we find this distance, we're going to be golden. The problem is that we don't know what Q is. We're trying to find Q. And so one of the best ways to figure this out is to recognize that that vector that we want to find is actually parallel, the same vector really, as the projection of the vector P0P. So this vector that's at an angle, that one's going to be acting as our U in this context. We will be projecting that down onto the normal vector. So this piece will be kind of our U1. That's the projection of U onto N. And then, it's not super relevant in this context, but U2 would be hanging out up here, the part that's orthogonal to U1 in an orthogonal decomposition. So that's the overall plan. We're going to project u onto n to find u1, which should be the same vector as the one that we're really interested in. Same magnitude, same direction. Okay. So here we are with that. We've got the normal vector picked out. We get to choose, any vector in the plane, and choosing 0, 0, -1 is one that works, where we just make the z value equal -1. And there again is the same labeling that I did. All right, here's a little bit more. So that vector p0 to p is 2, 3, 1. We actually had to, subtract to make that happen, given the p0 that we had as a starting point in the line and the point p that we had given to us in the problem as well. So it's important that we're using that vector p0p. That's our u. Then we've got our normal vector n, and we take the projection of u onto n. That's this calculation. And if we find the length of that vector, then we have the distance from the point P to the plane. And to find Q, we just take this difference between a couple vectors that we already have, 0p and qp, and when we take the difference between those, we get the vector 0q that we want. So there we have the vector version of q, and q is just that as a point. So there we go. We found the shortest distance and we found the point q. So we're good there. Now we're going to switch gears a little bit and talk quickly about the cross product. I believe we already talked about the cross product a little bit when we were talking about taking determinants. The cross product is really cool geometrically. When you take u cross v, you actually get a new vector that's orthogonal to u and v, and it's pointing in the direction, according to the right-hand rule. So if you get a positive number for the dot product, it's pointing in the positive direction according to the right-hand rule. If you get a negative, it's pointing in the opposite direction. Here's a mnemonic device for calculating a dot product between two three-dimensional vectors. There's a really cool video on 3 Blue 1 Brown that if you have not watched, I would definitely suggest that you watch and understand the cross product a little bit more deeply. There's actually a lot of depth there. There's actually 2 videos on the cross product. One that I would say everybody watch, and then the other one, linear algebra nerds, you got to watch it too. But yeah, really what the cross product is you're creating a new three-dimensional vector that's orthogonal to the first 2, and the length of that vector is the same as the area of the parallelogram generated by u and v. All right, so here we got a theorem. The cross product is orthogonal to both of the 2 original vectors, and the cross product is only 0 if v and w are parallel, meaning that they're in the same exact direction or they're completely opposite directions, because then the parallelogram generated by v and w would be, the area would be 0. All right, find all vectors orthogonal to both u and v. Here, we previously did this with the dot product, but now we could do it with the cross product by simply taking a cross product between u and v here. There's the mechanics of it, and we get the same exact vector that we did before. It was a little bit more involved with the dot products. This one made it seem simple. And yeah, really here, computing the dot product is just taking the determinant of that matrix, which it's a weird matrix. The 3 Blue 1 Brown video does a pretty good job of explaining why that works out the way that it does. It works out that way because of the duality of dot products. We could talk more about that in pronto if you want to. All right, so yes, any scalar multiple of that is also orthogonal, so we're great. Okay, I think that this might be the last major problem of the lesson, which is encouraging. We've got 2 skew lines. That means we are working in 3 dimensions. We've got 2 lines that are just zooming randomly through space. And these lines are not pointed in the same direction, and they're not touching one another. So these lines don't intersect anywhere. What we're going to do is we're going to find the shortest distance between those 2 lines. And the way that we're going to do it is kind of consider the direction vectors of those 2 lines and make a plane of sorts, you know, from those 2 direction vectors, you know, to get kind of like a parallel plane there, and then use the cross product to generate another vector that is orthogonal to both of the lines that we're given. And when we find that third vector that's orthogonal to the 2 direction vectors that we have, we're going to have the direction that we want in order to find the shortest distance. So here we go. We're going to do part A, where we're just looking for the shortest distance, and I think we're going to follow the plan that I just laid out. So our 2 lines have 2 direction vectors, d1 and d2. Those are in the equations of the lines. We take the cross product between those 2 direction vectors to get a normal vector, n. And then once we have that normal vector n, we project the line, we project the vector that connects P1 and P2, which are basically those starting points that we had for line 1 and line 2 respectively. So we take that vector and we project it onto the normal vector that is perpendicular to both of the lines. And when we take that projection, we get a vector and find that the shortest distance between L1 and L2 is, you know, that mess at the bottom of the screen. Cool? All right, and this is the second way to figure out what this distance is and actually figure out what the points P and Q are. So this is going to be a little bit different from just taking a cross product. But again, we start off with the 2 direction vectors. And really, let me get the marker out. This piece, the vector from, 0 to P is really just, I don't know, maybe the origin's out here. It's really just the vector version of P. But P is just some point on the line. And so the vector that you see here with the 3 plus s and the 1 plus s, that's given to us from the equation of the line. And similarly, we've got the vector 0q here. Now, if we take the difference between those 2 vectors, 0p and 0q, we actually find the vector PQ. It's just that difference. And then we can take the dot product between the vector PQ and the first direction vector, and then the vector PQ and the second direction vector. So this is a way of getting around using the cross product to find something that is orthogonal. Here we're using the dot product to find vectors that are, well, a vector that's orthogonal to both L1 and L2. But this works out really nice. They look like, a couple of linear equations, two equations, two unknowns. We know how to solve those. We could use, an augmented matrix. And we get the unique solution where S is -5/7 and T is 1/7. That means that we could plug S and T back into our original, lines based on, the vector formulation that we have up there. And we could get points for P and a point for Q. And again, if we found the distance between, P and Q there, if we found the magnitude of the vector PQ, we could find the distance between those 2 points. And it works out the same as the first one where we use the cross product. So that's really cool. That was a lot in hopefully a manageable amount of time for you to pay attention. I would challenge you to write a plan, just in your own words, on if you were to try to find the shortest distance between a point in a line or a point in a plane, or either in between two skew lines or something like that. Write down a short plan in your own words of like what projections that you would need to take in kind of what order to find certain distances. That is a good exercise that would help you process this. And again, we're going to continue processing this information on our activity that we're going to do on Friday. So I hope to post that to Canvas soon so that you guys could even possibly start working on it before Friday. But do plan on Friday. I will be on Pronto, ready to chat with you and help you work on activity 6, I think. So, this has been How to Math with Dr. Ian Lundholm. Remember, you have online homework to do. It's precisely homework 13 this time. And you're ready to do it now. I'll see you in the next video. Bye. Well, actually, I'll see you on activity 6. I'm going to see you on Friday. Okay, bye.